Apart from being asked to find the particle's position, velocity or acceleration vector, you may be asked some of the following types of questions. It's not an all-inclusive list, but it just shows you what they mean when they're asking certain types of questions and what to demonstrate in order to answer them. So firstly, when is the particle at rest? And the condition is when v equals 0. So in the one-dimensional problem, it would just be straightforward. You would set velocity equal to 0. But in 2 dimensions, you have to set each component equal to 0 and make a separate equation. So that's what we're going to do. I'm going to set the I component equal to 0, and I get t equals 2 seconds. And then the j component, 2t squared minus 8 equal to 0, so t squared equals 4. And just taking the positive value for t, we get t equals 2 seconds. And just to check that these are the same value of t, and so that's when the particle is at rest. Now, what happens if we get different values for t? So that you might get a question, show that the particle is never at rest. And the condition is that t is different when you set the components of velocity for I and j equal to 0. You get different values of time. So I've just changed this question. The j component is still the same. The I component, I've changed this to a 6. So now for the I component, I get 2t minus 6 equals 0, so t equals 3. And for the j component, as before, I get t equal 2. So it means that the velocity in the I direction is 0 at time equals 3 seconds, and the velocity in the j direction is 0 at time equals 2 seconds. So what actually happens is that you look at this, at t equals 3, velocity in the I direction is 0, but if we substitute that into the j direction, we get 2 times 3 squared, which is 18, minus 8, which is 10. So there's no velocity in the I direction, there's just vertical velocity of 10. And similarly, t equals 2, the j direction now will be 0, but the I direction will be negative 2, and so that would give a velocity like this. Next question, at what time does the particle reach maximum velocity? So once the particle reaches maximum velocity, it's no longer accelerating. So acceleration is equal to 0. So that's the condition here. And I have an equation here for acceleration. I just need to set this equal to 0. So I 2t minus 1 equals 0 gives me t equals a half a second. And for the j, 2t squared minus a half equals 0. So t squared equals 1/4 and t equals a half. So a half a second and a half a second tally, so the particle reaches maximum velocity half a second in. Next, show that the particle moves with constant acceleration. Now, if a particle moves with constant acceleration, it will satisfy the constant acceleration formulae. But we're showing that, so we can't assume that it does. And if a particle is moving with variable velocity, the constant acceleration formula won't work. But we can use the variable acceleration method for constant acceleration. So that's what I'm going to do here. So the condition is if acceleration is constant, then we get a value, a constant, for A. I have the equation here for the position vector. So if I differentiate this with respect to time, I get velocity, which is 3I plus 2tj. And then differentiating the velocity with respect to time, acceleration, the I component is 0 and the j component is 2, which is a constant. So I've shown that A is constant and answered the question. So a few more questions. when is the particle travelling parallel to either the x-axis or the y-axis? Well, if the particle has no vertical motion, it's travelling in parallel to the x-axis. So that's when the vertical component j equals 0. And likewise, if it's travelling parallel to the y-axis vertically, then the horizontal component, the I component, will be 0. So that's all we have to show. So if it's parallel to the x-axis, then we show that its j component is equal to 0, so t squared minus 4 equals 0, and that's taking the positive value, time equals 2. So at 2 seconds it's travelling just horizontally. We don't know which way because I haven't used the other equation. And if it was travelling parallel to the y-axis, then the I component, 3t minus 1, equals 0, so at time equals 1/3 second, then it's travelling vertically. So travelling, also should highlight this, is to do with velocity. If the particle is travelling at you're looking for velocity. When the motion of the particle, again, that's relevant to velocity. So when is the motion of the particle inclined to 45 degrees to the horizontal? Now, when a vector is at 45 degrees, it looks like this, and the components of I and j are perpendicular to each other. So this makes a right angle triangle with an angle of 45 degrees here and here. And so that must be an isosceles triangle. Therefore, the I and j component are equal. So all I need to do is set the I and j component equal to each other. 3t minus 1 equals 4 minus t. That means 4t equals 5, t equals 1.25 seconds. So that's when it's travelling at 45 degrees. So before I go on to the last part, just a recap on perpendicular vectors. If two lines are perpendicular, then when I multiply their gradients together, I get -1. So the gradient of a vector is the vertical, j, divided by the horizontal movement I. So the gradient of p would be 2/3, and I multiply by the gradient of 2, 3 over -2, and that does indeed give me -1. But also there's a second vector that's perpendicular. If I show you the original vector and multiply that by -3/2, I also get -1. Now why are there two? Well, if I show you this picture here, here's the vector p, 3i, 2j. Here's the first vector q, -2i, 3j, which is clearly perpendicular, but there can be a vector equal and opposite that's 2i, -3j, that's also perpendicular to p. So the question here is, show that for time not equal to 0, the particle's velocity is never perpendicular to its position vector. So velocity and position. I have position vector, I need velocity. So differentiate this with respect to time, and I get 4 minus 10ti plus 2j. And now I need to multiply these gradients together and show that I can't get -1. So I start by assuming that they are perpendicular. And then I'm going to show that the equation that I get has no solution, and so that they can't be perpendicular. So the gradient of the position vector is 2 divided by 4t minus 5t squared. and the gradient of the velocity vector, 2t, is 2 over 4 minus 10t. And if they were perpendicular, that would equal -1. I'm going to do a little bit of cancelling out here because I have to show this, so it's not going to be as easy as putting it into my calculator because my calculator won't give me an answer. So I want to make my calculations as simple as possible. Each of these is divisible by 2 every term, so I can so I can divide by t, and divide this one by t, so t squared becomes t. And then I'll write that here, so 2 over 4 minus 5t. And with the second vector, I can divide each term by 2, so 1, 2, and 5. And then I'm going to multiply both sides by the denominators of these. So 2 equals -1 multiplied by 4 minus 5t, 2 minus 5t. And now I'll divide both sides by -1, so that becomes negative, and this becomes positive. So I'll put a negative there and change that to a positive. So now I can just remove that. So -2 equals 8 minus 20t minus 10t plus 25t squared. And I'm just going to rearrange and simplify to 25t squared minus 30t plus 10 equals 0. And as I'm, again, can't use my calculator, I want to simplify this, so I can divide through by 5. And now I've got to show that there's no solution, so that these are never perpendicular. So I can use the quadratic formula, or I can just use the discriminant. So I'm going to show you with the full quadratic formula just as a reminder. So t equals minus b, so that's minus 6, plus or minus the square root of b squared minus 4 times a times c all over 2a, and this part here is the discriminant. So all I need to show is that the discriminant equals 36 minus 40, which is -4. So the discriminant is less than 0, so no solution. And if you put that into your calculator, you would get math error because there's no solution. So therefore we've proved that the gradient cannot equal -1 at all.